we are here today for using worked examples. I hope that's what you signed up for. And the reason why you're here, my name is Stephanie Kidd. I'm a math consultant here at KVEC. And Miss Vonda Adams is also here today. She's our math consultant at KVEC. But for today, we're going to work on just using these worked examples and what that looks like in every classroom.
I'm Vonda Adams, and like Stephanie said, I'm a math consultant here at KVEC, and I kind of work more toward the early elementary and elementary level, while Stephanie works on the middle school and high. We work together, of course, but that's our specialties.
All right, our objectives for today is why do we use worked examples? That's going to be a big one. What does the research say about it? What are worked examples and how do we use those? The types of worked examples, there's 4 of those, by the way. Create worked examples. We're going to actually create some, and that's how you're going to get your certificate, is you're going to create some worked examples and put them into a spot. And that way everybody has access to them. And then you have multiple ones for your grade level. And that's our hope for this training. And then, of course, how do we teach using those worked examples? Some things that we're going to think about while we're doing this. Well, one is, what is the concept or the procedure that you've recently taught? Think about something you've recently taught that you wish you'd had an example, a really good example for your students to use. And then what examples did you use in your lesson, and can we use those as a worked example possibly? And then how do you pick your examples? You know, is it just because it's in the book and that's the book I'm using? Is it something I saw on the internet and I thought it would be great? How do you pick those worked examples? Hopefully you're thinking with your kids in mind. And then how do you use your students? How do you engage your students with these examples that you're using? You know, is it just I'm working through them? Am I questioning my students? Those kind of things. And then how do you sequence the examples that you're using? Do you start with the most complex and then kind of hone in on just a specific misconception? Or are you actually starting with the simpler and moving toward the more complex? Those are questions that you can think about when we're going through this. How do I actually pick the examples I'm using? So just take a few minutes and think about the content you're teaching at this point in time, a worked example that you may want to create, or maybe you want to think about the content you're getting ready to teach.
And then, of course, you can refer to those structured notes that we sent to you. That was in the email that I sent yesterday evening. If you did not get that, so you can actually download that, use it as a Word document if you'd like, if you prefer to do it that way.
One of the things I want you to think about also is that Rachel Snyder suggests that when we use examples to engage our students in new content, and we make the content more accessible to the students by building on a key feature or procedure, we end up having less issues or less mistakes made by the students. So keep that in mind. And also examples, they help with the coherence and allow for conceptual connections. So we want our students to see this, and Ms. Vonda's going to talk about this in a little bit, but we want them to see the example that fits back with the conceptual part you're teaching. So, and we'll talk about that more, because examples can be procedure-based, and that's not how our students need to be taught in mathematics. So we're going to tie it all back in, we promise. All right, so why do we use worked examples? Well, this is a big question. One, limited working memory capacity. And if we think about our students, one of the things that they always have trouble with is processing speeds and their working memory. Now, working memory for a normal person is like no more than 7 bits of information at a time. So if there's only 7 bits of information that a normal person can handle, and we have a student who has a disability, that amount of information that they can handle at the time becomes smaller. So keep that in mind. So now, how do I make sure my examples are there so that my students not having to use way too much and be cognitively overloaded, and at that point just shut down on us? That's what we want to make sure that we're doing with these worked examples. We're not overloading them cognitively. Also, if you think about it, when we're using our working memory, It's just real small. It's not like our long-term memory where we can store bunches of information in it. Our working memory has to be entwined with some of the previous stuff that we've already done or that we already know to create strands in our brain. And in those strands, as they become stronger, at that point, that gets into the long-term memory because we make connections. We build on that schema. Now, if I go back to the limited working memory, what happens there is I have intrinsic, which is what's going on in my brain, and extrinsic, which is what's happening with the teacher. How did the teacher set these up? So that's huge because extrinsic is a form of our working memory load, and it's imposed by many elements. And like I said, it can be the part that the teacher's explaining, the presentation. Is there too much on that presentation that's taking away from other things? And our kids who have ADHD or have issues with being able to take in a lot of information, at that point, they get overloaded. So worked examples actually takes away from that cognitive load. And we work through one mistake at a time. Now, once we've built into this, and Ms. Vonda, like I said, is going to talk about this a little bit later, but she's going to talk about how we build this back into what they've already done conceptually. And when we do that, that helps them to not have to worry about just going through and doing the individual steps, but also they begin to understand those steps that they have to do, but to understand what's happening in the process. And then, of course, the last one is the automaticity that we want them to have, that fluency that we want them to have, but that develops when that schema has been completely developed. So making sure, so just to recap, what we're going to do is first, it's going to lighten their working memory load. And then they're going to recover and they're going to remove the focus from the computation to basically the strategies, and they're going to develop more accurately and more understanding. And then, of course, they're going to support the development and be able to explain it. That's what we want them to be able to do. Explain the process. And then last, of course, we're going to focus on one problem area at a time. So when we're doing these, that's going to be the big thing. Now, the ways we tend to think about math. First of all is procedural fluency. Well, unfortunately, procedural fluency should not be our focus. We should be going to the conceptual understanding. That needs to be first, even though most of the time we focus procedurally. We want to focus on conceptual understanding and then build into the problem-solving application of it. And this comes into play as they build the conceptual understanding. Students will display better cognitive or conceptual understanding after completing assignments that include analyzing correct worked examples and even incorrect worked examples. So we want them to work their way through it conceptually so students can be more accurate, they can be more flexible, they can be even more efficient. And then at that point, students will self-assess themselves in their understanding and the steps of the problem. At this point, they have procedural fluency. So at this point, we have, with worked examples, we're going to have arrows, we're going to have color coding, we're going to have lines, we're going to focus our students in on the math concepts that they need to develop. So that's all that we're going to do the entire time we're working through examples. All right, Ms. Vonda, I'm going to play your video, or do you want to talk first?
Go ahead and play the video, and then we'll replay it again, probably.
Okay.
As you can see, Stephanie's done a little doodly of the CSA model, and there's 3 parts. And you have the concrete, the semi-concrete, and the abstract. And you can see that under, when we're talking about concrete, we're referring to manipulatives. Manipulatives are what we call math tools. It's the tools that we use to explain. something to our students, it's tools we use to model, but most importantly, it's the tools that the kids use. We put these tools in their hands and they model. And it helps them to understand conceptually what concept we're trying to get across to them, whether it be in primary with addition or whether it be in high school, middle and high with algebra. We have tools that we use for algebra as well. So that's what we're talking about when we say concrete, and it's not something that's just done in the primary. And then we move on from that.
Let's go back to that concrete just real quick, because we use some of the same tools.
Mm-hmm.
So they need to keep that in mind too, that it's not always, I used a bead string in middle school. I used a bead string with my 5th graders. So it doesn't have to be something different or elaborate or anything else. So keep that in mind, guys.
True. And then, of course, after we have modeled and used those tools, then we have the kids link that to a semi-concrete where they would actually do drawings, or eventually then they want to be able to do those with mental images of what it would look like. And that's the stage that we spend. We normally we don't move from concrete and leave it. We take it along with us. And we have concrete and we move into the semi-concrete and we bring the two together. And then after we get really good at that, then we throw in the abstract. Now that abstract is when we're talking about using the numbers and those symbols. So lots of times teachers will make that mistake. They will go straight to the abstract and then they'll think, oh, well, they're not getting it. I guess I need to go back and show them how. And that's the wrong method. I mean, that's the wrong steps. First, we begin with that concrete, no matter what grade level we're working with. We move it into the semi-concrete and then to the abstract. Now, we actually created a model, and Stephanie, I did link that. If you want to click on up there where it's underlined CSA model, it'll take us to that. And you can see our work map. This is a work map that we created, and I'm going to drop this in a folder that we're going to share with you all at the end of tomorrow. And it will have, this is something you can print out, and we actually can use the tools. You see there's an area there, a space for the concrete, where you can actually have the kids build on that. And then they take that and then they actually draw a representation of what they built. And then when they're ready, they can write the number sentence, whatever they're working on, at the bottom for the abstract using those symbols. So it's a tool we created. It could be run on just a standard size sheet of paper, or we've actually put them on the really large legal size paper for the little ones that are working with those larger tools. All right, Steph, if you want to take us back.
I want to go back to this. If you've got somebody who's really struggling, and let's say they're not in special ed, let's talk about those kids that struggle. This is a perfect tier 3 for those kids. The CSA model is a perfect tier 3. Now keep in mind, you have to do all parts of it, but it is a perfect tier 3.
True. It's a great SDI. True.
Okay, Miss Vonda.
All right, I think we can advance on it. It may play again on you. That's why I was saying it may review it. Yeah.
Well, we can review
we'll try to advance. So again, concrete, that's the use of those manipulatives. Semi-concrete, that's those drawings and mental images. And then the abstract, that's when we use those symbols for representations and numbers. And of course, we do that at minimum 3 times, and then 2 times with that abstract. But that's the minimum that we want to give the kids. Most kids are going to need more experiences than that with it.
Yeah, definitely more experience than that.
Okay, now this slide is one that Stephanie found, just talking about using representations and multiple, and that's what we're referring to when we talk about that CSA model, or the multiple representations. And you can see on the left side is what the teachers are doing. Obviously, we have to be very careful about selecting tasks that will be friendly with the kids as far as them being able to use different tools or different ways to represent a task, to actually solve a task. And then, of course, it's talking about allowing instructional time. It does take time to do this. It takes a little more time to get those tools out and to organize them and teach the kids how to use them and instill in them that those are tools and not toys. That does take time. But I always tell everyone we can't afford not to take the time, because guess what happens? If we don't do it the first go around, we end up having to backtrack and go back and do it anyway. So why not do it the first time and get the kids going along? You're actually going to save yourself some time if you get the tools out and you'll work with the kids with them. We're introducing those different types of representations to the kids and that type of thing. That's what the teacher's doing. The students over here, they're making the decision about what tool am I going to need to use? What would I use to represent this? How would I represent this in a drawing form? Or how can I link this to what I've learned already? So that's what's going on with the students. And whenever I looked at this yesterday and I was preparing, it dawned on me, oh my gosh, this is our SMPs. This is the standards for mathematical practices right here in this form again. You know, we see so many different forms of it, so many different kid-friendly forms and that type of thing, but that's what this actually is. It's looking at, having our kids make sense of those problems. It's having them think about it abstractly and quantitatively, and they're having to, and when we get into talking about actually the worked examples, what those actually the kids have to do with them, you'll see even more of these SMPs. They're going to have to think about and critique other students' work. That's a big piece of that with worked examples. And then of course they're looking to see if did they attend to precision and did they choose the appropriate tools. And so it's really hitting on all of our standards for mathematical practice as well. So that's another bonus for using these with our kiddos.
Ms. Vonda, I also want to point out that this is also a great HLP 12 because it's a systematic design of instruction and it flows right through. And it's an HLP 15 with scaffolding or instruction.
Worked examples. Worked examples will emphasize a pattern. The kids will be looking for patterns when they'll either be looking at, like Stephanie said earlier, there's 4 types. No matter what type they're looking at, they're looking to see if they can make a pattern and make a connection to another problem whenever they tackle another one. It can go from conceptual learning, which is what we just talked about, to that structured procedural learning. Procedure, there's nothing wrong with procedure. We want our kids to learn a procedure, but we want them to understand why the procedure works, not learn the procedure first and then understand why it works. That's what happened to me when I first started working here. When I first started working with algebra tiles, Stephanie was showing me all these things, and I was like, oh my gosh, that's why that works. That should have never worked that way for me. I should have had an understanding first and then learn the procedure. All I knew was that FOIL method. I could do that. I could do that all day long, but I didn't understand why it worked. So that was such an aha moment for me, that our kids deserve better than just being taught a procedure. They need an understanding of it first. And then of course, it focuses on structural aspects for them to understand those concepts, looking at the different steps and not just looking at the steps and mimicking the steps, but understanding why those steps work in that procedure. So when Stephanie and I were planning on this, we really wanted to make sure that we drive home the importance of the conceptual understanding first, because we are not proponents of teaching kids procedure. That is not what this is about. This is about giving the kids examples and asking really good probing questions to get at that understanding. That's what this is all about today.
And also, Ms. Vonda, let's talk about the fact that this is about kids being able to explain what they're seeing that's happening.
Right.
This reminds me kind of your favorite video. The little girl who does 12 times 12. I know that. And she says, it's 144. I'll never forget that. And then what happens?
Then she can't explain it. She's been taught, she's just memorized it. That's a video referring to fluency, but she's not fluent. She just memorized it. She doesn't. Fluency means an understanding, being flexible with your understanding as well. So like I said, we most definitely want you to understand that we want you to go at this with the understanding that this is going to help your kids build that conceptual understanding as well. It's going to bring it along. Like I said earlier, it just really encourages them to think critically about the math and not just learn step 1, step 2, step 3, and so on, and how to mimic that with other problems. All right, so worked examples. They show a solved problem with visual prompts. For example, tests, arrows, color coding, or highlighting. And you'll see some of that in some of our examples that we've got for you here today and tomorrow. And they provide information about the problem-solving process. So it's information about that process. And here, especially for our kiddos, we want to think about for sure using those arrows and using that color coding. And I was thinking the other day when I was sharing one of these that I had done with Brenda, and I was talking about how that this is a perfect way to scaffold that. You give it to them with the highlighting on there, you give it to them with the color coding on there, and then you slowly just remove some of it. And the next time you may give it to them with a little less highlighting, or maybe remove the arrows. But we scaffold it and we just slowly remove that help that we give them along the way.
One thing I want to say with this, Miss Vonda, is if you're doing something like color coding for your students and it's in the worked examples, provide them with the ability to color code their own when they're working through them, because that will help. For my students, one of the things that I used to do was they had to write it in, if it was a negative, they had to write it in red. That way it really popped out at them. And so if they were writing that negative in red and they understood that, it was negative, that whole section was supposed to be negative, sometimes I would have them to underline it or to box it in red. That way it really popped out at them and they understood that. So keep that in mind. If you're doing it in the example, have them have the ability to also do that.
Right, and this supports, worked examples also supports that self-explanation principle, and that's where that the students self-assess their own work for their understanding. And then, of course, that just leads to greater gains. Whenever we figure out something on our own, we really can remember that much more readily than if someone just shows us how to do it. Or, because Stephanie, lots of times she'll come to my rescue when it comes to technology, because she's taught me so much in the past 4 years. But if I can spend the time and fumble around enough and figure it out myself, I remember it way better than what I do if she just comes over and shows me how to do it. So I like to relate things back to things that make sense to me. So you'll hear lots of analogies out of me today. That's the way I remember things.
It's also kind of like our shelf building. We remember how to do it because we struggled through it. It's part of that productive struggle that we have.
Exactly. Okay, so we have an effective method to improve learning, and there is research behind this. There's actually an article that Stephanie shared with you from What Works Clearinghouse that actually there was 4 studies that were done to prove that this is an effective method for kids to learn. And so it's not something we're just decided we like and we want to do it. There's actually research behind it, backing it up for us. So first of all, knowledge is gained from the example. It must be applied to solving a new problem, and that needs to come immediately. It's not show them a bunch of examples and then send them off to work. That's not what worked examples are. That's not how it works. You show the worked examples there, and there's lots of probing questions that go along with it. And then they work a sample problem just like it. And then you present example and then similar problem right after. Sorry, I jumped ahead of myself. So that's the next step there. And then effective problem solving rules are formed when target problem solving can be guided by an accessible source example. So if you'll think about it, I was thinking about that yesterday, like I said, when I was reflecting back on this. I always reflect back to my own learning. And I can remember those old textbooks that we had, and they would put the sample problems in there for us. And we would look at some of the sample problems, and then you'd come across that one that there was no sample like it. There was no example for me to look at. And I was one of those procedure gals. Like I said, you show me a procedure and I'd do it. But there would be those one or two that you just couldn't find anything to help you out with. And I was thinking, that's what teachers do sometimes to their kids. They'll do that sometimes. They'll give them, they'll show them examples, and they'll work through samples, and then they'll throw them for a loop and throw something in there that they've not even seen before. So the good thing about this, that's not what this is all about. This is all about showing them those worked examples, then asking those really good questions and making them think about the thinking that went into those examples, and then giving them a problem that, for lack of better words, is parallel to that, because that's one of the types that you can immediately go and apply that knowledge that you gained. So that's pretty much the scenario of how that's going to work.
I think the big key here, Miss Vonda, is the fact that they need to provide similar problems, and that similar problem needs to be, if you're focusing on a specific skill or a specific concept, that is definitely what is put there in front of you. You don't want it to be off in any way, including if I've got middle school, high school teachers here, including down to if it's got an exponent in it, the next problem will have an exponent in it, so that they follow through. So keep that in mind.
Right, right. And think about that. If you know, I mean, if you've been teaching the same grade for 3 or 4 years, you know what kinds of problems the kids are going to get hung up on. You know what's going to happen. So why not go ahead and make those your worked examples? Put those problems out there for the kids and go ahead and help them to work their way through that. You know they're going to hit that bump. Go ahead and smooth it out for them. Help them along the way. So that's whenever Stephanie referred to the task we're going to ask you to do for us tomorrow. That's what I want you to be thinking about as we finish up today and work in tomorrow. Think about the areas that your kids have trouble in math. Think about what you've seen, and think about what kind of problems you could put out there to help them get over that little hurdle that they're going to come across.
But also, if they're doing these problems, make sure they're different enough to where they don't get confused in it too. So an example is, if you've got 2 with the square root of 2, you don't want them to think that it's 2 times 2. So the next one, if it's 3 to the square root of 2, 3 squared, I'm sorry, I said that wrong. If it's 2 squared, you don't want them to think it's just 2 times 2, and they're just timesing those, that they really understand if it's 3 squared, that it's 3 times 3. So making sure they understand that. So giving them something that they're not going to get confused on is another big thing too, or that they can get hung up on.
Right. And once we get into those incorrect examples, you'll see how that can really take care of that issue with you too. So like I said, once we get to those types. Okay, go ahead and advance us on, I think. No, go back one. There we go. I like this one. I like this slide. Note that worked examples are not the same as working examples. Because when I first heard of the term worked examples, I thought, well, that's what we all do, isn't it? We all work examples for our kids. That's not what this is. Worked examples are examples that are already worked out. The solution's there. We're not asking for the solution. We're asking, how did they get to that solution? That's the good thing about worked examples. We're wanting to know the how and the why, not the what, as in what is the answer. So that's the good thing about worked examples. So bear that in mind while we're working at these. And of course, the kids are constantly analyzing and reasoning and trying to figure out why they got what they did. And in the case of the incorrect, they're trying to figure out why they got that wrong and what could they have done to fix that. So lots of good questioning has to go along with this examples. That's the hard part when you're developing these. When I developed them for us for tomorrow, that was my hard part, was coming up with the questions that I would ask the kids. It wasn't the examples. I knew what I wanted to work on there, but what kind of questions would I ask to get my kids to explain their thinking and the understanding that I wanted them to have?
I also like the fact that worked examples provide students with the ability to self-assess their understanding of what's going to happen
Mhm.
next. So, and am I doing that part? So that's a good thing about worked examples.
And then, of course, we have this quote here from William Paul Thurston: mathematics is not about the numbers, equations, computations, or algorithms. It is about understanding. And that should be our motto, I think, Stephanie. That's what we're all about. It's about the understanding, making sure our kids understand all along the way, all the way up, building that foundation and making sure that they understand what's underneath before we start layering more on. Because as we all know, we're only as strong as our foundation. So that's, and lots of times our kids will hit those bumps. I talk about how that whenever kids, there'll be those perfect students, those high flyers that I call them, all the way through, uh, especially through elementary. They hit into that middle and they get into that eighth grade and they may get into that pre-algebra and that algebra and those concepts, and they just hit a wall because all they've done all along is procedure. And they've been those perfect little students. You show me how, I'll go do it. You show me how, I'll go do it. But don't ask me to tell you how I got it or why it works that way. I just know it works. They don't like to explain their thinking because they really don't understand it well enough to explain their thinking.
Vonda, I found that once students get out of high school and go into college, that ability to think of why this has happened, they don't understand that. And they have issues when they're in college
Mm-hmm.
because they're not taught the process of understanding why something is done. They're just show this procedure and this is why you
Mm-hmm.
do it. And a big example was the geometry part. I know when I went to high school, my teacher taught me the theorems, and we had to write a theorem about why we did such stuff. And I don't know if they do that today or not. I haven't seen that yet because I've not been at the high school level to see anything of what they're doing in geometry. But I do know those theorems need to come back because they need to understand why this is
Mm-hmm.
parallel to that, or why this is congruent, or what does congruent even mean. They need to know those pieces to better understand why. So when they get into college or they go into some kind of field that involves math, they can explain why this has happened.
Mm-hmm. Absolutely, yes. And that's, like I said, that's that's our main drive. That's our main concern with putting this training out here today, was we didn't want people to think that we're supporting just putting a problem out there and kids copying and looking for to see if they can just make it match. That's not what we're looking. That's not what it's all about. It's about the understanding that we want to come uh, prior to giving them that representation, that abstract representation. And then it's about the understanding, as in asking those really good questions, as in why and how did you come to did they get that answer? Or why or how did they get it wrong?
Or being able to self-assess and ask themselves those questions.
Right, right. Of course, self-assess, that's big. If our kids can self-assess and they can realize that they've got something wrong and then figure out why they got it wrong, then and then self-correct it, that's where we want them to be. That's what then they become lifelong learners, because then they can learn, okay, I can figure out when something's not quite right. So I know that I just have to keep working at it, that productive struggle we mentioned earlier, until I can figure it out and get it down pat, and then it becomes just routine for me. So that's what life's about. That's what it's been like for me. It's been lots of productive struggle.
Okay, you had an article. It's called Learning Algebra from work examples. Now, what I want you to do is I want you to think about that article that you read. It stated that most growth in students' learning was found in the classroom environment in which students considered both correct and incorrect examples. I want you to take a minute and on your structured notes page, I want you to just jot down somewhere that what your thoughts are about that and how you plan to incorporate this. And we're going to kind of share out in just a few minutes. We're going to put you in some breakout rooms for about 5 minutes, Ms. Vonda.
Yeah, I think that should be plenty of time.
Think for about 3, and then we're going to do some breakout rooms. One of the things, I'm going to talk about a couple of things with this worked example. One is when I think about worked examples, I think about the students' understanding that they're going to have. And the big thing that hit me in this article was one strategy to correct students' misunderstanding is combining the use of worked examples in the classroom with students' self-explanations. So making sure that that is a big part of it, making sense of that new information, the student needs to talk it through. And then the other thing was that one of the big misconceptions they had for algebra for later was the equal sign, guys, just thinking that an answer comes at the end of it. And so that seems to be a big problem all the time when we talk about algebra. I have teachers that are like, they just think that it's an answer at the end of the equal sign and it's not a balance. And so having that there. Another thing that I highlighted in this, for those of you who may not have got to read it, was that already completed problems helps direct attention to certain steps of a task, and that it focuses on questioning. So worked examples is going to focus, believe it or not, on the questioning that we're going to ask throughout. And then another thing that I really hit was it encourages students to identify the reasoning behind each step. So if anything that we're doing, it's the reasoning behind it. Again, that's those whys and how questions that we really, really want to focus on.
Right. And then too, I want to mention there the reasoning, when you mention reasoning, using those incorrect examples really, really fosters thinking about why. Why is that wrong? What did they do wrong? How could they have corrected that? Or how could they have done that differently to get that right? It's like we call it non-examples in our primary world, but just using those incorrect ones are very powerful. And some teachers are, in some of the research that they were doing, are afraid to show them an incorrect way to do it, thinking they'll do it that way. But if you show them it's incorrect and you tell them it's incorrect, that's when it's powerful. They have to know that it's incorrect. That way they know to look for what went wrong, why it's wrong.
And that was my next thing. Miss Vonda just jumped right on.
Sorry.
But it focuses this, if you think about incorrect ones, it focuses the students to think about the steps that have been carried out and the reasons why those actions were wrong. Why was those actions wrong? What did they do that caused that misconception? And then it confronts their own probabilities of a misconception they may have, especially when you're talking about it and you're going through it. That's the reason why also I love the parallel one, or the one that we're going to talk about later where it's partially completed. So if they're making a mistake somewhere, that partial completed will be the one that we really want to focus on maybe. So
partial completed may be better.
So, we've got some options, and that's the reason why we want to talk through all these different ones.
Because our kids are all different, right?
Oh, yeah.
And what works for one doesn't always work for all, or what works for all doesn't always work for that one.
And something else that you brought to mind, brought to my attention, talking about concrete and abstract. Years ago, I became familiar with hands-on equations, and I think it works great. And I use it a little bit. We didn't have the program, but I had some family members in another district that had it, and I used it, and it worked really well because it became that abstract became concrete. Mm-hmm. So I get what you're saying with all that. That works.
Yeah, it's really true. I'm not just telling a story. Yeah, it was a major aha moment for me. It really was with the algebra tiles.
Yeah.
And I came in already using the algebra tiles at my school because we were blessed enough to gear up and bought those for each one of our kids, and we had class set. And so I had used those, and I seen what my kids could do using those. So it was like, oh, these are so wonderful. We use them. We saw a big difference in our kids, and especially my kids, because then it wasn't, I guess it wasn't a stigma that they were using some kind of a tool or something, because all the kids were using them, right? So if everybody has the opportunity to use them, you can use them at any point. And we would walk around the room, and me and my co-teacher would be like, a student was struggling, go grab the algebra tiles. Didn't matter who it was. You know, if they were struggling a little bit, go grab the algebra tiles, show me how to do this.
That's a good point, Stephanie, you made that I forgot to make earlier, was that we use these tools with all students, because our special ed students are gen ed students first. All students benefit from using that CSA model. And first of all, mainly because it helps everyone learn and understand. And then the bonus is that it removes that stigma about using tools. Just because you use a tool doesn't mean you don't understand it. We're all using the tools.
And I was so blessed to have a co-teacher who was like, this is our room. And we both kind of taught at, you know, at different times. And so if I was better at something or he was better at something, then we both were, you know, would teach, you know, different areas. But another thing was, he was like, carpenters have tools. He's like, doctors have tools. We all at some point use tools. And that was his big thing. These are just tools that we're using. And so that really helped for our kids to see it's okay for me to go grab a number line, or it's okay for me to go grab my algebra tiles if I need them. That was a big aha moment for us, seeing the kids just really want to get into that. So another thing that really hit me was, there's a part in this article that it talks about students that struggle, and this helps them when they're analyzing, and they're more gainful in their understanding. So keep that in mind with this too. And then there's a part, I'm going to hit it real quick. It talks about incorporating worked examples into the classroom offers a way for students to confront their own misconceptions and then to replace them with a better, deeper conceptual understanding. So keep that in mind too. So that's one of the reasons why we wanted to do this. Training was for you guys to get that, you know, it is all about, again, going back to that conceptual understanding and tying it in. I'm going to go ahead and talk about that What Works Clearinghouse that we had talked about before. There were recommendations for that one, and it was using solved problems to engage students, and analyzing algebraic reasoning and strategies was a big part of that. And it was to teach students to utilize structure, especially with representations. And then the other thing that article had in it was to teach students to initially choose from alternative strategies when solving problems. So those were some big ones for that article too, because I don't think that we actually go and hit on that one a whole lot. But it is a great article for you to look at. So make sure you go back to that one.
Yeah, and the important thing about that, and the reason I mentioned this, is just that it is research-based. This is a strategy that's research-based, and that's important, especially when we're working with our kids and we're thinking about the SDI that we're going to offer to them, that it be something that's research-based.
Types of worked examples. Now, we've already talked about several of these. We've talked about correct examples and incorrect, and we also talked about just a few minutes ago about partially completed examples. But there's another one that's in there, and that's parallel examples. So I'm just going to talk real quick about the fact that if we're working with correct examples, that's it. They need to be correct. You may scaffold those correct examples in many different ways. Like I said before, color coding, highlighting, arrows, those kind of things. Those are all in there. And we're going to show a couple of those today. Now, incorrect examples, with those, make sure, it doesn't matter what kind of example it is, make sure it's marked correct or incorrect, and the students know ahead of time. That's going to be the biggest thing that you need to remember, besides the fact that they need to be arranged a certain way. So making sure that you can do that. But correct examples need to be labeled as correct.
Yep.
Incorrect needs to be labeled as incorrect, needs to be somewhere on there kind of big and bold.
Yeah, that is not the task. It's for the kids to determine whether it's correct or incorrect. Do not give them that task. That is not the purpose of this.
They won't know the difference.
That's right. Exactly. Exactly. So that is not the intent of this. You make sure that they're labeled big and bold, correct or incorrect.
And keep in mind, this is part of your design of your instruction too. So back to that HLP 12, the design of the instruction. When we're going through that, you're going to design your instruction, and I would always start with a correct example. Just because of the fact you can choose whether that correct example is going to be very complex or if it's going to be very simple, and you're going to look at one specific area that you know that's going to be a misconception, but making sure that it is a correct example that you start with so that they know what steps are there, what procedures that they may need, that they've tied it back into whatever they've been working with concretely.
Yeah, and it needs to be something that's simple anyway, because you're going to, the first time you give them one of these, you're going to teach them, it's going to be about the process.
Mhm.
How do I engage with this? Correct examples. What are these? You know, how do I answer these questions? That type of thing, because it's going to be different for them if they've never been exposed to them. It's going to ask them, because always before we've been asking for the answer. Now
Mhm.
we're not asking them for the answer. We're asking them how they got to the answer. So that's going to, so like Stephanie said, I'd use something really simple to start out with the kids, just to introduce them to the concept. So, you know, it's like playing a game. You play a game 2 or 3 times with kids just for them to understand all the rules and how to do it before you expect them to learn anything from it.
And this can be part of your learning goal, is walking through those and answering those questions. It can, and you're going to teach toward this, yes, them getting correct answer, but understanding why that answer is what it is. So problems need to be geared, like I said, toward a specific learning goal. You're going to make sure it fits whatever that example needs to fit whatever your learning goal is. And then making sure that, again, it's identified correct or incorrect. And your prompts need to be that you're going to have, you can call them prompts, you can call them questions, but those have to be a guide for you and a guide for the student to look, places to look at. You know, it may be in line 2, why did this happen? In line 3, how do you know that when I add these 2 numbers that this is what I get? So those kind of things. So making sure also that the students are going to have to talk themselves through it. Ms. Vonda, do you want to talk about parallel and partial?
Are we not going to go through the slides?
We can.
Let's just do it as we go through the slides.
Okay. So in this one, research suggests that when mathematics is limited to a set of examples to be completed, this is part of your structured notes too. Instead of a set of examples for the students to understand, students may be more focused on completing the problem than making sense of the set of examples. Basically, what it's saying is if I'm working toward an answer, I'm not always understanding why or how I'm getting to that answer.
Yeah, they're focusing on the what again. They're focusing on what the answer is, getting to the answer, instead of focusing on why that works or how does that work. Again, that's just procedure.
Step 2, why could I not just skip that part?
Mm-hmm.
For many kids, it's like, why did I have to do that step? Or sometimes they don't know what's missing in their problem. And this helps them to understand that. All right, correct examples. This is a good example of a correct example. It says Kim solved the problem correctly. Again, it says it's a correct example. It says she solved it correctly. So we know that she did this. One of the things that I left out of here when I was doing these, and I thought, wow, I should have put that in there, was the fact that there probably should have been 1/2 and 12/1. So the students understand that 12 is truly 12 parts. You know, it's truly 12 over 1. But in this case, I'm working on through it. I do this and I go down here and I am, if we were doing this with our manipulatives, they would see how this works out and how that 2 is 2 out of the 12 and how that breaks on down into 6. But, you know, we've done this several times with some manipulatives. What half times 12? What's half of 12? And they would break them apart, half of 12, move them up, and they would get 6. Now, in step 3, why do you think she changed the 12 to a 6 and the 2 to a 1? And so you can talk about that. And you would walk the students through that. And then you would give them a problem again that looks exactly the same. So your turn for the students, as you can see, we've completed the first part of it, which is just basically rewriting the problem. Now, what are we going to do next? And the student can go through, rewrite the problem, work it out, and come to the correct answer. And they have the same right side of them.
Now, notice the important piece of this, though, is that question at the bottom where you ask why. Why do you think she changed the 12 to 6 and the 2 to 1? That's the important part of worked examples, are the questions that demand that the kids think about how and why.
And what's that process that they're having. So that's the part where we're going to get into of what kind of questions can I ask? What do I need to? And again, it's going to be a lot of why or how, those kind of questions. Incorrect. Again, it's marked incorrect. If you notice, I've got 1, 2, and 3. These are the steps basically that they're taking. You want to make sure they're laid out that way for them. And you want to make sure that they have the opportunity to see each step in its entirety. So in this case, we've got 46 milliliters plus 25 milliliters. And we broke this down into 40 and 6. So, and 20 and 5, because maybe that's the way that they need to do this. This is incorrect. What happened here that's incorrect? Now, this could be a kid who doesn't count up correctly, has some issues with counting up, those kind of things. Well, of course, 6 plus 5 is not correct. And then they would talk about that. Where do you see the mistake and how did it change the answer? That's the question down here. Where do you see the mistake? How does it change the answer? And so we would talk about at this point, this should have been an 11. If I go down here and I correct it at the bottom, and that becomes 60 plus 11, and then I have 71, they can talk about that. And then again, they're going to do their turn over here with the same exact type of problem, making sure that they put the milliliters at the end. We would talk about that.
And of course, they're numbered. And the reason they're numbered so that you can refer to those lines. Like you may ask the question, in line 2, what mistake was made? And then, of course, the kids back in their answer, they could say, if you left it like this, where did you see the mistake? Then the child could reply in line 2. They could identify where the mistake is at. So that's the purpose in numbering those as well.
Okay, so parallel.
All right, parallel examples. Just move on to that next slide and I'll talk about it. Says we use parallel tasks to differentiate instruction. So why not use parallel examples? So think about that. We use parallel tasks. So why not use those parallel examples when we're teaching the kids math? So you actually have a little notebook down there. So that is something on your structured notes. I try to remember to point that out because I forget myself. I think it's just a little fill in the blank. So Steph, you can move on. All right, let's look at this parallel. Notice that they're both labeled correct. And it's bold and it's in red and there's no mistake. They don't have to think about, well, is there a mistake here or not? And in this case, with the parallel, the problems are exactly the same as in, you know, how it's written out, but the approaches are different. The approach they took is different as into how that they solve the problem. So that's the approach with this parallel one. With another parallel, another way you could do a parallel is you could do a correct and then an incorrect, if you wanted to. You also could do a correct, and then you could do another same type of problem as a correct. And they could look at two different ways, two different types of problems, but they're both going to be correct. So there's different ways you could set up a parallel examples. As you can see here that they've just done the multiplication is different. What they decide, their first step is different, is what they've done, is what's different on this one. And of course, you'd ask those kinds of you'd ask that kind of question. You could ask, for example, why did Mike choose to multiply 4 times x and 4 times a -2 in line 1? So you could be very specific about where you want the kids to look at. Where do you want them to look? And that's another good strategy also for, which especially when you get into the parallels and the partially completes, you want to put a fictitious name to it. You want to put, come up with some kids' names, or use your own name if you want in those places.
Big thing with that, one also with this one that my kids would probably have trouble with. And I would say in Mike's, in line 3, how did he get -6?
And so that could be a question, like Stephanie just said. How did Mike get -6? And think about, you had to think about it. You had to really look and think, okay, what did he do to get to that? And you don't have to think about whether it was right or wrong either, because you know it's correct, because we told them it was correct. That's the good thing about making sure they know that they're correct or incorrect. So we talk about all the time how there's more than one way to get to an answer. Mm-hmm. So this is an excellent way to show the kids how to do that there's more than one way to get to that final answer down there. There's there's more than one way for me to get to hazard. I'd come down 15, or I'll go around and I'll come up 80. There's more than one way for me to get to this office. So there's more than one way to solve a problem. And so if that's your goal is for the kids to understand that, then this is what you would use, this type of example.
And for some kids, it may be easier to do Mike's way, but in other kids, it may be easier to do Lisa's way. Mm-hmm. So you need to think about that, because not all kids think the same way. So
right.
And multiple ways to do some things. Sometimes things click for them. Well, that's a new way, or that's easier for me to see. And so they can do that.
Right. Well, I spent 30 some years in primary, and I spent the beginning of my years with doing a lot of procedure, because that's all I knew to do. That's what I was taught, and that's what we told to do. But when I started working with math intervention, I felt the same way too. I thought, oh my gosh, how in the world would I get these kids to understand this whenever I start trying to make them look at it with place values, what we're actually having them to do when we do that. But after doing it, because I had to do it and seeing it, and I worked with intervention kids, it does work, because what it does is it forces them to think about the meaning behind it. It really works on their being able to do mental math, because we want them to be able to do 42 plus 12 mentally.
Oh, yeah.
That's our goal. So that's why we make them break it apart and look at the place value pieces of it. That's the reason behind it. It's not that we want to make them have to do tons of steps. We want to move away from the steps as soon as possible to where we do it mentally. Those types of problems.
Yeah, and I love it because I think mentally, and this is an activity that Vonda and I actually did with some parents, and you take just money and you give them like different things of money, and then you say, okay, now sort it and then count it. And where do you start? Well, you start with the bigger numbers. Well, in this case, why are we teaching our kids to start in the ones place? Because they don't have to. So going back to that and thinking mentally, if I'm adding something up, where do I usually start? And I start with whatever the biggest number is in that case. And if it's 600, then I'm going to start with the 6, and I go that way. But that's mentally how I do it. But also I have an understanding of place value. So you got to keep that in mind too.
Mm-hmm. Right. So if you think about it, like Stephanie said, if you had some cash, you're fortunate enough to have a handful of cash. Nowadays, people don't have a lot of cash, but if you had some cash you needed to count, and then you start with those greater bills first. That's where you start, and you work your way. And when we teach that traditional algorithm, that's not the way we start. We start in one place, and we regroup, and the kids really don't think that, they don't understand that that's a 10. They think that's just a 1. They're sticking up there with those other numbers and that kind of thing. So that's why we really want them to see the place value piece in it.
And it's really hard for us when we start doing this because of the fact that we were taught a procedure. You got to think of it that way. Okay, Miss Wanda, your next one is partially complete examples.
Dana Johnson left a message in the chat, and she was talking about what Brandon was talking about earlier about learning all these new ways, you know, and then trying to build on multiple approaches. So she left a message in the chat, and of course, Brandon, you responded back to her.
Right, and of course you're right. Those basics, those fluency, fluent to 5 in our kindergarten, fluent to 10 in first grade, fluent to 20 in second grade, and by fluent I mean fluent.
Right.
To where you're not having to use your fingers, you're not having to use a lot of time, you're being flexible. When you're fluent, that's when you can do the next step.
Yes.
You're right.
That's where we're missing them right there.
Absolutely.
Right.
We have to make sure they're fluent. Absolutely. Absolutely. I did not intend to insinuate that at all.
Oh, no, I didn't think
that's when my kids that's when they would take off. When we were fluent, especially when we're fluent to 10. Wow, can you do a lot whenever you're fluent to 10? You have a huge understanding then. And then whenever you're fluent to 20, you're ready to go. Because it relieves all that, you know, that working memory that Stephanie was talking about earlier. You don't have to worry about that because it's there. But you're right, absolutely. You've got to make sure they're fluent. And I have tons of activities with that. And I've got a lot on our website that you guys can visit if you want to look at some things, some activities that will strengthen that fluency. And I don't care a bit to meet with someone. If you want to email me, and we'll set up a Zoom and I'll share with you.
Again, Vonda, when we talk about that fluency, though, what have we done so much to get to that fluency is nothing but conceptual. They've played with blocks, they played with counters, they've done so much, and they've talked it through. So they have to do those things. They have to have those in their hand. They have to have all kinds of different stuff that they've done several times, talked it through, drawn it out. They have to do that.
Yes, all of my activities are not worksheets. You won't find a worksheet with anything I do with anybody, ever. It's not. You might find a recording sheet, but there's always tools that have gone along with it. That's how I teach. That's what I believe, and I'll go to my grave believing that we have to do that. We have to get the tools in the kids' hands. And then it comes just like that. Enough tries, and they can do it. All right, I'm off my soapbox.
Well, you can partially your soapbox with partially worked examples. All
right, partially worked examples now. Notice again, they're labeled correct, both of them. And Stephanie put together this slide for us, and she did a good job color coding for us. So you can refer to all your questions can be asked as far as referring to what's in red or what's in blue. Jessie, what did Jessie do in step 2 in the red? Those types of questions. But you can see that with Jessie's work, there's part of it's been left out. The blue, step 3, is incomplete. That's what we mean by partially worked. Just steps have been left out. So you've got to look at what comes before, look at what comes after, and then plug in what's missing. They're puzzles.
Where did you got the 70 from?
From the 30 and the 40. See, again, again, we think place value. You got to think, okay, that's 38 books and 49 books that I've got in my pocket. So if I want to count all that out, I'm going to count out the 10s, or, you know, I may have 20s in there, but I'm going to put my 10s together first. Then I'm going to worry about those single bills.
And if you notice, we color coded the red circle with the number 2.
Mm-hmm. So you think about, okay, that 70 came from that 3 and that 4, which is 30. Actually, not 3, but it's 3 10s and 4 10s, which gave me 7 10s, which is 70. So now I've got to think about my 1s. I've got 8 1s and 9 1s, which gives me 17 1s. So they would think about what's missing there. And of course, in Mike's, in Mike's, the 10s are what's missing. The 40 and the 30 are what's missing there. So the partially worked examples are a really good way. I would think that I would want to use those after I've tried the others. I would want to work with my correct and my incorrect, and I'd want to look at my parallels, because partially worked, they're like puzzles. You're looking for missing pieces. So to me, that would be the one that would require a little more understanding in order to tackle those.
This would be a really good one if you're working in middle school and you're doing the order of operations. I like that for that. Of course, with that, you have to keep in mind that students may not always follow through, and there's different ones. So there's different ways. And then of course there's my way that I do with the river. And so there's multiple ways that you can do those if you're working through them. But the big thing is, like Vonda said, this is helpful to see the missing step, what would happen next. And then of course, how do you know? That's a good question. How do you know that's the step that's missing for our kids? And what helped you to determine what needed to go on line 2 or line 3? So that way you're getting that self-explanation in there. All right. So you have this little funny Stephanie's thrown in here. Says, what do you expect? My edition of the math book doesn't have answers in it like yours does. So that's what the kids think. That's why the teachers know everything they know, is because they've got all the answers in the book. But, you know, I thought about this and I thought, you know, that's might be part of what the problem is. They need some answers. They need some worked examples in these books. They need to rewrite these textbooks, if you're lucky enough to have a textbook, and put those examples in there. But it says a picture example always reinforces a concept. And that's the main goal we want you to come away with today, is the value of these worked examples. And yes, there are different types, and it depends on, like anything else, it depends on the child and their ability and what their misconception is, which type you would want to use with them. So that comes back to you just knowing your children and knowing what they need. So as Ms. Vonda has talked about, a picture or an example is always reinforcing the concept. So why do we not use full examples for us to use for our students? And that's what we're going to talk about more today. Now, points to consider when we're teaching with worked examples. First, you need to name that strategy. Make sure that you give it a name, whether it's worked examples or it's solve problems. But then the next thing is we have to explicitly teach it. Now, that's part of that SDI.
I want to stop right here, Stephanie, on that, and make sure that we reiterate that we have to explicitly teach what we're giving these examples of. This is not in place of explicitly teaching it. We have to make sure that we've taught it. This is a way for us to monitor it and see if they're getting it, if they're understanding. It's not a way to teach.
Exactly. But we have to explicitly teach this. So as SDI, it is specially designed instruction. So it's instruction on how to work through or to work with a worked example. So if I've got a worked example there, we need to make sure that we are explicitly teaching how to use that worked example in everyday activities that they're doing. Now, the other thing is to model using a previously taught content. This is a good reteaching moment. So keep that in mind. It can be used to bring in new content, but it's really, really, really important to think of it as a model for previously taught content. So this is a good time right before we give a formative assessment to bring these examples out and walk through them. Third thing is use Think Alouds. Identify the how and the why. Again, the how and the why is what we're going to do most of our questions with. It's not going to be the what. We're not looking for an answer. The answer's already there. We want to know how, or why they did the next step. And so you're going to be looking at those steps and strategies inside that problem. And then, of course, incorporate this into your instruction. This can be a bell ringer. This can be station teaching. This can be done as a whole group. It can be done small group. And so keep that in mind. These can be incorporated throughout your instruction. They're not, oh, we're just going to do this today.
It's not a worked example day. It should flow beautifully. It should not be something you stop and throw in one here and there about this and that. It should work to enhance your lesson.
Exactly. And also embed this in independent practice. So another thing is, I was incorporating into instruction, if you've got a student who is really mastering that concept, let them be a teacher in it too. So that's another thing to consider. All right, steps in creating worked examples. Ms. Vonda, you want to go over this one?
Sure. Like I'd asked you before in day one, I asked you to determine a standard that you wanted to work with. That's selecting that goal. That's what that's referring to. And you're going to gear that problem toward a learning goal with common student errors in mind. When you choose that standard, I want you to think about the errors that you know that your kids are probably going to make. It's things that you just, you anticipate, so you pre-correct it. If you expect it, you pre-correct it. That's from coming from Anita Archer there. Then you select a type. Determine, it depends on what your standard is, what you're trying to get across to the kids, what type of work example you're going to use. You're going to either use that correct one, or you may use a parallel or a partially complete. And we feel that those incorrect ones need to be hold off on those until you feel the kids are getting it and understanding it. And it's a good way of checking them for their understanding, especially when you're doing a review, to make sure that they still understand what you're trying to get across. So those incorrect ones we don't want to use too early on in our lessons. And then of course you select your prompts and make sure that they're numbered and labeled clearly. Make sure they're labeled correct or incorrect, and make sure that the questions you ask are intentional, that they're going to guide the student's thinking from step to step. And of course, you can think about how you might need to scaffold this. You may need to use color coding or underlining or arrows or highlighting, and depending on what the kids need. And of course, those are the types of things that you can remove once you feel like the kids are comfortable with working those types of problems.
Exactly. And just remember that scaffolding, when you're taking that away, take away one step at a time. Don't try to take all of it away, because that may be a problem.
Now, it's truly what a scaffold is. You don't remove it all at once. You remove it a layer at a time. And of course, the highlights of what we've talked about here. We've talked about the research. You've read some of the research that we have found, and it all supports that worked examples enhances that student learning. And it is an effective approach for real world, for classrooms. The examples that we give, the scenarios we give, they need to be something that the students can relate to. Anytime we can relate something to the real world, the kids are more interested in it, especially if it can be something that's current going on in the news, or something that's current for or appropriate for their age or grade level or whatever their interest is. That's what we need to try to do with our problems. And of course, having students explain incorrect examples helps to improve conceptual understanding. If you have a child that can explain why something's incorrect, then that child will be able to explain that to another student. So that's a child that you could pair up and use a little peer tutoring with. And there's nothing wrong with peer tutoring. Peer tutoring just solidifies and it enhances the learning and the understanding of the one who is doing the tutoring and the one that the child is working with. Because lots of times those children may be able to relate to a peer when they can't relate to an adult that's in the room.
Okay, and now it's time for you guys to actually work on your problems. So what we're going to do is we're going to break up into different groups, and we're going to work on, if you're K5, you'll go with Miss Vonda, and if you are middle school or high school, you'll stay with me. Thank you.
Elementary portion of worked examples. And what I have in front of you, what you should be seeing on your screen is a copy of that CSA work mat that we shared with you on day one. I just wanted to talk about this briefly before we get into those 4 types and looking at them just at an elementary level and how that we can adjust it down to working with kids that are working at that level, whether they're in elementary or not. But this CSA work mat is just what I had said earlier, is designed for you to use your manipulatives, and it can be used for simply just building a number. Like I've got my base 10 blocks out here just to model for you all just briefly. Like if we wanted to have the children model the number 23, then they would pull out that mat. You'd pull out your cubes. If they choose to use these tools, there's other things you could use. You can model with bundles and sticks. You can model with Unifix cubes, just different types of things to model of building a number. But and then of course, after you've done this, they've modeled with the manipulatives, the concrete portion, then you move into that semi-concrete, and that is where they actually draw the representation of what they see. And then after that, then they will move into that abstract. Of course, this is just a child working on identifying numbers and understanding place value is what this would be if we were working on it. Okay, so any questions on that? Because I just want to briefly show you that because I want to model that for you and show you. So that is actually one of those documents that I put in there for you all to use. I had these when I had my children work. I didn't have this. I didn't develop this until I came to KVEC. But if I were using this with kids myself, I would put this into a sheet protector and have them use a dry erase on it. I don't do that because it causes a sheen and a glare with the document camera when I'm modeling for everyone. So any questions on that? All right. If you have questions, just unmute and talk to me. You can drop it in the chat, but sometimes it's hard to see the chat whenever I'm sharing my screen this way with the document camera. All right. So this is the first of the examples I want to share with you. This is an example of a correct worked example. And you can see what I did is I made this template, and then I chose to do it by hand as far as the work goes because I wanted it to look real world. I wanted it to look like something that that another child had done. And of course, this child I've named is Sam. So this is Sam's work. And notice how I've made point that it is correct. It's correct work. And then we're just working on 38 and 47. And of course, if we're working on adding 38 and 47, we've already talked about expanded numbers. Therefore, we know how to expand 38 into 30 and 8, and we know how to expand 47 into 40 and 7. So that we've already gotten to that point. So we're just taking what we've learned and building upon it. So that's some prior knowledge the kids would have. And then we would talk about, okay, you want the kids to notice that we've had some experience using parentheses as well. So we've talked about that with our kids prior to giving them a worked example that looks like this. So notice the questions here at the bottom. Like I told you on day one, this is the most important piece, is that questioning that we put with it. So our first one, of course, I've got, why did Sam expand 38 and 47 in line 2? So what was the reason for that? So what do you all think I'm looking for there? What do you think I would want them to say? Any thoughts on that?
I don't really know where I would answer.
Okay. I appreciate that, Brandon. That's right. That's fine. But if the kids have already talked about expanding numbers and they've understood that we're looking at 10s and we're looking at 1s, then hopefully they would know that we expanded 38 and 47. So we could, in the next step, put our 10s together and then our 1s together. So that's what I'm looking for. That's what I'm getting at. And of course, this is something that I would have worked with my kids on prior to. And then of course, the next question says, how did he get 15 in line 4? Just want to draw their attention back to line 3. Okay, how did he get that? And of course, obviously you can see that he added 8 and 7 to get 15. And then how did the use of parentheses in line 3 help him to solve the problem? So how did those parentheses help him out?
It helps keep them separated.
Exactly. It helps keep them separated. It separates our 10s from our 1s. Exactly. To prevent them from doing it this way, you could show them this way. You could set your 38 plus 47 up this way. 30 plus 8 and 40 plus 7. You could set it up this way.
That looks better.
And they would know to add their 10s and their 1s. Okay. Generally, what we do, and of course, you're working with kids that have already been through this, just didn't quite get it. But generally, when in the primary, what we want them to do is look at problems horizontally first, and then move them to a vertical representation. And the reason we don't do this first, when we give a problem to them in primary, is because somebody wants to show them the algorithm, and they've stopped thinking, and they want to show them to start in the 1s place. And that's not what we want them to do. We want them to think about 10s first, then 1s. So that's the purpose in looking at it horizontally. But this can be done this way. Okay, I'm going to share the second correct example with you. Oh, I forgot. We didn't talk about the matched problem. And of course, notice the matched problem is one that requires them to do some regrouping per se. There's going to be too many 1s that they're going to have to come up with. They're going to have a 10 here that they're going to have to think about putting together with the other 10s. So it's the same type of problem, same type of scenario, just using different digits. Okay, so when you're doing a correct example, what you do is you give them one, you show all the work, you come up with those questions, those probing questions to think about, and of course you ask those questions in mind, keeping those errors that they might make in mind. Because notice I wanted to draw attention to the 15. How did they get 15? So I wanted to make sure that we pulled that out. And so hopefully they'll apply that to the one that they work. So like Stephanie said earlier, this would make a good bell ringer once you have covered the content. It's something that you just want to do as a review with them. I firmly believe that bell ringers should only be work that we're reviewing that we feel that they've got. We just don't want them to lose. Okay, here's the second one. It's along the same lines, except this one, I think this was the one I intended to show first. I've got them in reverse order. This one doesn't require them thinking about that 10 in the 1s is what this one is. But notice the questioning. Same type of problem. The only difference was that the first one I showed you required it was going to give them an extra 10 there. So my question here is, why does Sue expand 42 and 35 in line 2? Again, I want them to tell me that we want to look at the value. We want to look at the 10s, and then we want to look at the 1s. And then why does she group 40 and 30 together in line 3? Well, she wanted to put her 10s together. And then she wanted to put her 1s together. And then why does she group 2 and 5 together in line 3? Again, how and why questions is what you want to think about. And then, of course, another match problem. Notice that the 5 1s and then 4 1s would only be 9. So we're not required to think about that 10 when we group our 1s together. Any questions on correct worked examples? And were you all able to open up that link that I shared with you?
Yes.
Good. Okay. I'm always paranoid that I have not set that to where it'll open for people. All right. Let's look at some incorrect. Even though we said incorrect would be something we would probably use later on, we'll go with the flow of how we presented them to you. So this is Jill's work. It is an incorrect example. Now notice how I put incorrect in red. I want to make sure the kids know that this is not correct. And I'm drawing on past experiences here. This is what some of my kids would do whenever they did not understand. When they would do this, then I knew that they did not understand place value. But whenever I saw my kids do this, when they would expand 39 into 3 plus 9 and 56 into 5 plus 6 and hundreds, I knew that they did not understand the value of that 3 in 39 or the value of that 5 in 56. And that's another reason why we have our kids to expand numbers, so we can make sure they understand that that is 30. That's 3 tens, not just a 3. And then, of course, that's what my questions are. I'm going to lead them to finding what mistake did Jill make in line 2. And hopefully they would be able to tell me that that 3 should have been a 30 and that 5 should have been a 50. And then what should she have gotten when expanding the numbers in line 2? Then I would want them to tell me or show me what she should have put there. And then how would you explain that to Jill? This is going back to that part where I'm talking about the kids being able to teach the others. If you understand it well enough, you can look at someone else's work and explain to them what their mistake was and how to correct it. So that's what I'm getting at with that question there. And of course, it does have a matched problem where they would need to be doing the same thing. Expanding those numbers, grouping your tens and ones to find the sum. And of course, this could be used with other things. It can be used with building numbers. It could be used with subtraction, multiplication, division. I just wanted to gear it down for us just so we could see that worked examples can be used at the elementary level. Most research has been done with around algebra, but we can take it, and I think it would be a great teaching tool with our kids. So this is the incorrect worked example, just using 3-digit numbers. Bob's work is an incorrect example. And you can see that right away, hopefully, what happened to Bob, that he still doesn't have an understanding of place value. He does not understand the value of the 2 in 241 or the value of the 4 in that number. And the same thing with 536. So again, I'm asking for what mistake did Bob make in line 2? And of course, he's not written the correct value for those digits. And then again, I'm asking what should he have gotten? I mean, I'm repeating these questions, just a different problem. And how would you explain the unreasonableness of his answer to Bob? I mean, look at that one. Look what Bob ended up with. He's saying that 241 and 536 is 21 by using the method that he used. So that's another thing that we always need to ask our kids about, is that answer reasonable? Does that make sense? Because if it doesn't make sense, that's a clear sign that we've made a mistake somewhere along the way. Then, of course, there's a match problem. Any questions or comments on the incorrect worked examples? So let's look at parallel then. Now remember, the parallel is we're working at 2 problems side by side, and you can set them up differently. It depends on what you're trying to get from the kids. It depends on if they're ready to look at a correct compared to an incorrect. It depends on if you want them to see 2 correct. And of course, you could do more than 1 if you wanted to. You could put 3 on there if you needed to for them to look at. You also could use the same problem. As you can see, that's what I've done here. I've got Katie's done this problem correct, but Jack's is incorrect. And then, so So that's what I'm doing here. But like I said, you could very well have 2 correct on here. You could have 2 incorrect on here. Whatever you want to do with the kids, it's up to you. And also it depends on what the content is, what it lends itself best to. But in this case, Katie is subtracting 638 and Jack minus 254. And with Katie, you can see that we have already talked to the kids about when we subtract and when we add and subtract numbers, that we work with our greatest value first. That's what we do when we're working with money. That's what we do if we were going to think about it mentally. So that's why we want to look at it that way. So I've got 600s minus 200, and that would give me 400. And then I have 3 10s, and I'm subtracting, and I got a negative or subtracting 5 10s. So that's how I end up with that minus 20 there, is that 3 10s minus 5 10s is going to leave me with a negative 2 10s, or I'm going to be needing 2 10s. That's how I explained it to my little ones, is that, well, I didn't have enough, so I needed 2 more 10s. Okay. And then, of course, 8 1s subtracting 4 1s would leave me with 4 1s. And then when you think about it, 400 minus 20, again, this comes back to being able to do that mentally. 400 minus 20, well, 100 minus 20 is 80. So 400 minus 20 would be 380. And then I'm adding that 4 on. Okay. Now this takes lots of work with your kids for them to be able to do things this way. You may have to begin with expanding the numbers. This is a problem that's after we move beyond expanding and looking at the expanded form for each number. And then the questioning, why did Katie begin subtracting in the hundreds place first? Of course, we want to talk about how that's the greatest place. That's the place that has the greatest value. So that's where we want to begin when we subtract. And how did Katie get that negative 20 in line 4, or minus 20 in line 4? And then we would talk about how that we were trying to subtract 5 10s from 3 10s, and we needed 2 more 10s. And then if you look at Jack's incorrect response, you can see that with my questions, what was Jack's mistake? So I would want them to be able to pick out and tell me where his mistake was at. And you can see that his mistake was in line 4. And notice how I've got those. That's the purpose in getting those lined up, so they can tell me exactly where they found that mistake. In line 4, that should have been minus 20 instead of 20. So that's where he messed up. And what are some similarities between Katie's and Jack's work? Well, in the hundreds, they both have, when they subtracted 600 minus 200, they've got that 400. In the ones, 8 1s minus 4 1s, they've got that 4. So that part they understand. The part that Jack is having trouble with is when that top add-in, that digit in the top add-in is lower than the digit on the bottom when he's subtracting. And so he's not understanding that regrouping. If we were going to do this as a regrouping algorithm, he's not ready for that. He's not understanding that there's not enough there. He's just doing what the kids would, and it's a common error. If it won't work one way, they'll do it the other way. They'll subtract top from bottom or bottom from top. So the last one I want to share with you is the partially completed. And with this partially completed, I'm going to turn my tray around. I use some color coding. Oh my, that's blurry for you. All right, so you can see what I've done here is I've used some color coding. And I have, so what I have is I have color coded. Line 1 all the way across is blue. Line 2 all the way across is yellow. And then line 3, of course, is red, and line 4 is green. I'm going to move that down so you can see the whole thing. And I'll just tell you what those numbers are. This is Jane's work, Tom's work, and Dale's work, and it's partially complete. So with a partially complete, then obviously there's been things left out. So in Jane's work, line 3 is where her work has been left out. And of course, this is multiplying, and it's thinking about using that area model with the kids. And where if we expanded 15, as in 10 and 5, and then on line 3, we needed to expand 24, and that would be, of course, you can see what's missing in Jane's work is we need a 20 up here for 20 and 4. And then, of course, you would fill in the work. 20 and 20 times 10 would be 200. And then 20 times 5 would be 100. And then you could think about what the question in here is what factor and products are missing from line 3. So that's all I would need to know is for them to, they would have to be able to do the work to answer this question. And then how did you determine the factor in line 3? So how did she decide, or how did you decide what Jane needed to put in line 3 as far as the factor? Now notice I'm using that terminology. I'm using the words factor. I'm using the word product because we want our kids to know what those words are. And if we don't use them, then they're never going to remember them. So we have to use them. Now, you're going to may have to have a word wall. You may have to fix them a little notebook that has a list of vocabulary in it, but we need to make sure we use those words. Now, another way to scaffold for the kids, if they needed it, then you could, on your document somewhere, on your template, you could put what factor is and what product is to remind the kids of what those words mean. And then you could remove that. This is one of those where we could eventually move the color coding, remove it, and have it just as a blank form for the kids as well. And of course, the next one, Tom's work, what factors are missing from line 2? You can see that he needs to expand 26 into 20 and then 6. And how did Tom determine the product 24 in line 4? So in line 4, I want to know how he got that 24. So he would have to take this number. He'd have to know the work from here and multiply that 6 times 4 to get that 24. And then Dale's work is 41 times 12. And notice all these problems are very similar. They're just 2-digit problems by 2-digit. And our questions here, what factor and products are missing from line 4? Now, there will be some what questions, by the way, when you get into doing the partially, because you're asking for an example, and then you want to know how you get to that. So what factor and products are missing from line 4? Again, we're filling in what's missing in the green. And then how did Dale get 10 and 2 in line 2? Going back to how did he get that 10 and 2? Well, that's from the 12 where he expanded it. I like to give 3. When I say I like to give, I would just think that it would help if you had 3 different ones to look at instead of just the 2. But again, that's your choice, and it depends on what your kids need. If it's something that's going to overwhelm them, then by all means, only give them 2. Or you might want to just give them 1 that's partially worked and ask them and guide them, and your questions would guide them to filling in what's missing. If this is too busy, too much, then cut it down to just 1. Cut this thing apart. You could even do that. Cut it into strips. But what I'd like for you to do is take that template, one of those, if you'd like to, or if you want to create your own, by all means, you can do that. And think about whatever standard that you are going to be working on next, or whatever one you think will benefit working or reviewing with your kids. And you're going to choose to do either worked examples, a correct one, an incorrect, partially correct, or parallel. We'd like for you to choose and do 2 of those. You don't have to do all 4, just 2 of them. And then you will email those to us. And then once we receive them, we will send you an email back. Like all of you that are with me today, right now, will send them to me. And everyone that went with Stephanie will send them to her. So I will then send you a link to do a little evaluation for us. And then it will, as soon as you submit that, it will shoot you a certificate. Okay.